So this is part 3 of the Physics 2 final exam review series. So let's start with this problem. A 20-volt AC signal is applied to the primary coil of an ideal transformer which has 100 turns. So the primary side is on the left side. So here we have 100 turns. The current that is flowing in this coil is 10 amps. The secondary coil of the transformer has 1000 turns, and so that's on the right side. Calculate the output voltage and current at the secondary coil. So here's the formula that you need to know. The number of turns in the secondary coil divided by the number of turns in the primary coil, that's equal to the secondary voltage divided by the primary voltage, which is equal to the primary current divided by the secondary current. So what you need to know is this. As you travel from the left side to the right side, notice that the number of turns increases by a factor of 10. The secondary voltage will increase by a factor of 10 relative to the primary voltage. However, the secondary current will decrease by a factor of 10. This is known as a step-up transformer because it increases the voltage. So let's write down what we know. On the left side, the primary voltage is 20. The primary current is 10 amps. And the number of turns in the primary coil is 100. Our goal is to calculate the source voltage, but the secondary voltage and the secondary current. Now we have the number of turns in the secondary coil, which is 1000. So as we said before, because the number of turns increases by a factor of 10, the secondary voltage will increase by a factor of 10. So the voltage at the output will be 200. The current is going to decrease by a factor of 10. So it's going to be 1 amp on the right side. Now you could use the formula to get these answers, but because the ratio between the two coils is a nice number, there's no need to use the formulas. You can get the answers mentally. So that's it for part A. We have the secondary voltage and the output current. Now what about part B? Calculate the power absorbed by the primary coil and the power delivered by the secondary coil. Power is equal to voltage times current. So in the primary coil, the voltage is 20, the current is 10. So the power that's absorbed by the primary coil is going to be 200 watts. In the secondary coil, the voltage is 200, the current is 1. So notice that the power is the same. This is due to the law of conservation of energy. Every second, 200 joules of energy is being absorbed by the primary coil, and 200 joules of energy is being delivered by the secondary coil every second. So the rate at which energy is absorbed by one side of the transformer is equal to the rate at which energy is delivered by the other side. And so that's it for this problem. Number 2. A 10 centimeter long solenoid has 280 turns of wire and a cross-sectional area of 0.10 square meters. Calculate the self-inductance of this coil. So let's draw a picture. So we have a solenoid with many turns of wire, and we have the length. It's 10 centimeters. And our goal is to calculate the inductance of this coil. The inductance is going to be the permeability of free space times the square of the number of turns in this solenoid times the cross-sectional area divided by the length of the solenoid. So the permeability of free space is 4 pi times 10 to the minus 7. The number of turns is 280. The cross-sectional area is 0.10 square meters. Now the length of the solenoid is 10 centimeters, which is 0.10 meters. So these two numbers cancel. So it's going to be 4 times 10 to the minus 7 times 280 squared times pi. And so you should get 0.0985 henries. So if you divide that, or rather if you multiply that by 1,000, that's the same as 98.5 millihenries. So that's it for part A. Now what about part B? How much energy will be stored in the magnetic field created by this solenoid when a current of 10 amps flows through it? So we could use this formula. The potential energy stored in an inductor is going to be 1/2 Li squared. So the inductance we got is 98.5 millihenries, or 98.5 times 10 to the minus 3 henries. The current that's flowing through it is 10 amps. Now don't forget to square it. So if we plug this in, we're going to get this answer. The potential energy stored in the magnetic field is going to be 4.925 joules. And so that's it for part B. Now what about part C? Calculate the induced EMF generated by this solenoid when the current decreases from 10 amps to 0 amps in 0.05 seconds. So here's the formula that we need. The induced EMF is going to be negative L times delta I divided by delta T. So the EMF generated by this solenoid or any inductor is based on the inductance and how fast the current is changing, either increasing or decreasing. So the inductance is 98.5 times 10 to the minus 3 henries. Now the change in current, the final current is 0, the initial current is 10, so the change in current is negative 10. The change in time is 0.05 seconds. So it's negative 98.5 times 10 to the minus 3 times negative 10 divided by 0.05. So the voltage induced will be positive 19.7 volts. So that's how you can calculate the induced EMF of an inductor. Number 3, a 12 volt 60 Hz AC signal is applied to a 100 microfarad capacitor. Calculate the capacitive reactance. So let's begin with a picture. So here is our AC signal, and it's directly connected to a capacitor. So it's 12 volts and the frequency is 60 Hz. And here is the capacitance represented by the symbol C. The capacitive reactance is XC. It's equal to 1 divided by 2 pi f times the capacitance. So the frequency of the signal is 60 Hz. The capacitance is 100 microfarads, and micro is 10 to the minus 6. So it's 1 divided by 2 pi times 60 times 100 times 10 to the minus 6. And so you should get 26.526 ohms. So that's the answer for part A. Now part B, what is the current? The current is going to be, it's very similar to this equation. V is equal to IR. In this case, we have V is equal to I XC. Capacitive reactance behaves similar to resistance, but towards an AC circuit. So the current is going to be the voltage divided by the capacitive reactance. The voltage is 12 volts. The capacitive reactance, 26 0.526 ohms. So this is going to be 0.452 amps. And you could say that's the same as 452 milliamps. So that's it for number 3. So that's how you can calculate the current of a circuit like this. Number 4. A 200 millihenry inductor is connected in series with an 800 microfarad capacitor. At what frequency will the capacitive reactance equal the inductive reactance? So here we have an inductor, and here we have a capacitor. The inductive reactance is XL. The capacitive reactance is XC. So we want them to equal each other. The inductive reactance is equal to 2 pi FL, and the capacitive reactance is 1 over 2 pi FC. So if we put this over 1 and cross multiply, this is going to be 1, and that's going to equal 2 pi times 2 pi is 4 pi squared, and then we have F times F, which is F squared, and then LC. So our next step is to divide both sides by 4 pi squared LC. So we have 1 over 4 pi squared LC is equal to F squared. Next, we need to take the square root of both sides. So the square root of 4 is 2. The square root of pi squared is pi. Now we can't take the square root of LC, so we'll leave it like that. The square root of F squared is F. This is known as the resonant frequency. It's the frequency at which the capacitive reactance is equal to the inductive reactance. So let's plug in the information that we have. So L is 200 millihenries. So that's 200 times 10 to the minus 3. C is 800 microfarads. So that's 800 times 10 to the minus 6. So go ahead and plug that in. Now, if you're not getting the right answer, it may help to put this entire thing in parentheses. So this is what I have. 12.58 hertz. So this is the resonant frequency of the circuit. And so this corresponds to answer choice A. Number 5. A 12-volt AC signal with a frequency of 1 kilohertz is applied to a series RLC circuit containing a 100 ohm resistor, a 30 millihenry inductor, and a 3 microfarad capacitor. Calculate the voltage across the inductor. So let's begin with a picture. So here is the AC signal, and it's attached to a resistor, an inductor, and a capacitor. So we're going to say this is R, L, C. We have a 12-volt AC signal with a frequency of 1 kilohertz. What we need to do in this problem is calculate the voltage across the inductor, which we'll call VL. So let's talk about what we need. The voltage across the inductor is equal to the current flowing through the inductor times the inductive reactance. Now, in order to calculate the current, we need to take the voltage of the source, or the AC signal, which is 12, and divide it by the impedance of the circuit. The impedance, represented by the symbol Z, measured in units of ohms, is the square root of R squared plus XL minus xc squared. So let's calculate XL and XC first. So XL, the inductive reactance, is 2 pi FL. So that's going to be 2 pi times the frequency, which is 1 kilohertz. Kilo is 1,000, so that's 1,000 hertz. And then times the inductance, which is 30 millihenries, or 30 times 10 to the minus 3 henries. So let's go ahead and plug this in. So the inductive reactance is 188.5 ohms. So let's save this value for later. Now let's calculate the capacitive reactance. So the formula for that is Xc is equal to 1 over 2 pi Fc. So it's 1 over 2 pi times 1,000 times the capacitance, which is 3 microfarads, or 3 times 10 to the minus 6 farads. And so that's going to be 53.05 ohms. So now we have the capacitive reactance. Now we can calculate the impedance of the circuit. So the formula that we need is the square root of R squared plus XL minus XC squared. So the resistance of the circuit, we can see that it's 100 ohms. So that's R. The inductive reactance, we have it already. It's 188.5, as we can see here. And the capacitive reactance is 53.05. So go ahead and type that in exactly the way you see it. So I got 168.36 ohms. So that's the impedance, which I'm just going to rewrite it here. So now once you have the impedance of the circuit, you can now calculate the current flowing in the series RLC circuit. So as we said before, the current is going to be the voltage of the source divided by the impedance. So we have a 12 volt AC signal, and we're going to divide it by 168.36 ohms. And so the current is going to be 0.07128 amps. So now that we have the current flowing in the circuit, we can calculate the voltage across the resistor, the voltage across the inductor, or the voltage across the capacitor. Let's say if we want to calculate the voltage across the resistor, it would be the current times the resistance. If we want to calculate the voltage across the capacitor, it's the current times the capacitive reactance. But for this problem, our goal is to calculate the voltage across the inductor. So it's the current times the inductive reactance. So it's going to be 0.07128 amps times the inductive reactance of 188.5 ohms. So the answer is about 13.4 volts. So answer choice E is the right answer. Notice that the voltage across the inductor exceeds the AC source, or the voltage of the AC signal at the input. And this is completely possible when you're dealing with series RLC circuits. So that's it for this problem. Number 6. A traveling electromagnetic wave has a magnetic field with a strength of 2.5 microteslas. What is the strength of the electric field of this EM wave? So what formula do we need for this problem? The magnitude of the electric field is equal to the velocity, or rather the speed, of the traveling EM wave times the strength of the magnetic field. Electromagnetic waves, they travel at the speed of light, which is 3 times 10 to the 8 meters per second. The strength of the magnetic field is 2.5 microteslas, or 10 to the minus 6 teslas. So all we need to do for this problem is simply multiply those two numbers. And so the electric field is equal to 750 newtons per coulomb, which also has the same units as volts per meter. So answer choice C is the answer. Number 7. What is the wavelength of a FM radio wave operating at 101 megahertz? So what formula should we use in this problem? The speed of light, or the speed of any electromagnetic wave, is equal to the wavelength times the frequency. So the wavelength is going to be the speed of light divided by the frequency. The speed of light we know to be 3 times 10 to the 8 meters per second. The frequency of this radio wave is 101 megahertz. Mega is 10 to the 6, so it's 101 times 10 to the 6 hertz. So all we need to do is divide those two numbers, and that's going to give us our answer. So the wavelength is 2.97 meters. So that's how you can calculate the wavelength of a radio wave given the frequency. So B is the right answer. Number 8. The speed of light in a certain type of glass is 2 times 10 to the 8 meters per second. What is the index of refraction of this material? Now this problem is not bad, just like the other two problems. There's only one formula that you need to know. The index of refraction, represented by the symbol n, is equal to the speed of light in a vacuum or an empty space divided by the speed of light in that material, in this case, in the glass. The speed of light in empty space is 3 times 10 to the 8 meters per second. However, light slows down when it travels in a certain medium. In this case, in glass, in this particular type of glass, light is 2 times 10 to the 8 meters per second. So its speed was reduced by a third. Now we could cancel 10 to the 8, and we could also cancel the units in meters per second. So all we're left with is 3 divided by 2. 3 divided by 2 is 1.5. And so this is the index of refraction of this type of material. So C is the answer. Number 9. A light ray is incident upon an air-water surface at an angle of 40 degrees. What is the angle of refraction as the light ray enters the water layer? Well, let's begin with a picture. So that's the boundary between water and air, and this is going to be the normal line. So on top we have the air layer, and on the bottom, water. The index of refraction for air is 1. For water, you could look this up, it's 1.33. Now a light ray, I'm going to draw in red, is going to basically strike the boundary between air and water, and then it's going to refract. Basically, refraction is the way light bends as it moves from one material to another. So this is the first angle, the angle of incidence. It's between the incident ray, which is this, and the normal line. The angle of refraction is between the refracted ray and the normal line. Now the formula that we need is referred to as Snell's law, also known as the law of refraction. So N1 sine theta 1 is equal to N2 sine theta 2. So the left side, we're going to use it for the first material, which will be air. The right side, we're going to use it for the second material, which is water. So N1, the index of refraction for air is 1. The incident angle, we know it's 40 degrees. N2, the index of refraction of water is 1.33. So we need to calculate theta 2, which is the angle of refraction. So let's get rid of this and let's put 40 degrees here. So what we need to do right now is divide both sides by 1.33. Sine 40 divided by 1.33 is 0.4833. And so that's equal to sine of the refracted angle. Now to calculate that angle, we need to take the arc sine of 0.4833. And so that's going to give us the second angle. And so you should get an answer of 28.9 degrees. So that's how we can calculate the angle of refraction in a problem like this. Number 10. What is the critical angle between the interface of water and air? When will total internal reflection occur in this situation? So let's draw a picture. In order for total internal reflection to occur, the light ray has to travel from a material of high index of refraction to a material with a low index of refraction. So in the case of air and water, it has to start from water and travel to air, and not air to water, because water has a higher index of refraction to air. So it's going to start here, and then it's going to bounce off. Now, total internal reflection will occur if the incident angle is greater than the critical angle. Now, when the incident angle is equal to the critical angle, the refracted angle is going to be 90 degrees. So let's say this is the critical angle. Then the refracted angle will be between the air-water boundary. It's going to be between air and water, so it's at that boundary. And this will be 90 degrees. So we need to calculate the critical angle in this problem. So let's use this formula. N1 sine theta 1 is equal to N2 sine theta 2. So the left side is going to be for water, and the right side of the equation we're going to use for air. The index of refraction of water is 1.33. And theta 1 is going to be the critical angle, which is what we're looking for. The index of refraction of air is 1. And then theta 2 is the second angle, which is 90 degrees. Now, sine 90 is 1. So what we need to do is divide both sides by 1.33. So sine of the critical angle is going to be 1 divided by 1.33, which is 0.7519. So now let's calculate the critical angle. So it's going to be arc sine 0.7519. And so the critical angle, this is the rounded value, it's about 48.8 degrees. So total internal reflection will occur when the incident angle exceeds 48.8 degrees. And so when this happens, there's not going to be any refracted angle. Keep in mind, when reflection occurs, the incident angle is equal to the reflected angle. Number 11. An object is placed 12 centimeters from a concave mirror with a focal length of 8 centimeters. Where is the image located? So we have the distance between the mirror and the object, that's DO, so that's 12 centimeters. The focal length is 8. And we want to find where the image is located, so we need to calculate DI. And here's the formula that we can use. 1 over DO plus 1 over DI is equal to 1 over F. So we have 1 over 12 plus 1 over DI is equal 1 over 8. The best thing to do is to eliminate all fractions. I recommend multiplying both sides by 24 DI, because 8 and 12 can go into 24. So 24 DI divided by 12, that's 2 DI. 24 DI divided by DI is just 24. And 24 DI divided by 8 is 3 DI. Now the next step is to subtract both sides by 2 DI. And so on the left side we have 24. On the right side, 3 minus 2 is 1. So 1 DI is the same as DI. So the image is 24 centimeters away from the mirror. So that is where the image is located. So that's it for part A. Now let's move on to part B. Calculate the image magnification. The magnification can be calculated using this formula. It's negative DI divided by DO. So it's going to be negative 24 divided by 12. So in this case, the magnification is negative 2. So that's it for part B. Now, part C, if the height of the object is 4 centimeters, what is the height of the image? Now, it's important to know that the magnification is the ratio of the image height to the height of the object. So the height of the image is going to be the magnification times the height of the object. So that's negative 2, and the height of the object is 4 centimeters. So negative 2 times 4 is negative 8. So the height of the image is negative 8 centimeters. So now at this point we can answer some questions about the image. So part D, is the image real or virtual? What would you say? The fact that DI is positive tells us that the image is real for a concave mirror. Now what about E? Is the image upright or inverted? The fact that HI is negative tells us that the image is inverted. If HI was positive, the image would be upright. Now what about, is the image enlarged or reduced? In order for the image to be enlarged, the absolute value of the magnification has to be more than 1. If it's less than 1, then the image is reduced. So, because the magnification is negative 2, the absolute value of negative 2 is 2. And so that's greater than 1. And so we can say that the image is enlarged. And basically, you can compare the image height with the height of the object, and the image height is greater than the object. It's about twice as tall, just in the other direction. And so it tells us that the image is enlarged. Now, let's draw a ray diagram. So we're going to say the focal length is, let's say, here. And so that's 8 centimeters. So the object should be somewhere in this region. So we're going to draw a light ray from the object. It's going to strike the mirror, and then it's going to bounce back towards the focal point. Now the second ray is going to start from the object. It's going to touch the focal point, hit the mirror, and then reflect back this way. Now notice that the rays intersect at this point. So this is where the image is. Now, Because the actual light rays converge, we're going to get a real image. Sometimes the light rays may appear to converge, but it do not actually converge at that point. That will be the formation of a virtual image. And you would see it using dashed lines instead of a solid line. So if you have a solid ray, or rather two or more solid rays converging at the image, it's a real image. If you have dash light rays converging, then it's a virtual image. Now notice that the image is facing in a downward direction. So that tells us that we have an inverted image. Now this is not drawn to scale, but you can see that this image is taller than the object. So that tells us that we have an enlarged image. And so that's how we can draw the ray diagram for this particular type of problem. Now for those of you who want more examples on problems like these, including how to draw ray diagrams, I recommend that you go to the YouTube search bar, type in ray diagrams organic chemistry tutor, and you're going to see a lot of videos come up related to that topic. So feel free to take a look at that when you get a chance, and don't forget to subscribe to this channel. Thanks again for watching.